Hello. Good morning to all of you. Let us start the class.
Good
Uh,
morning, sir.
we have, yeah, it is pretty cold in this side, and probably today is the coldest day in this winter. Maybe I don't know, but it is very cold. Anyhow, so let us start the class. In last class, what I taught you is the just review your quantum mechanics QFT of MPC 302 part. So this, what are the things we have learned, what we supposed to learn there, and basically the canonical quantization, meaning of canonical quantization. Canonical quantization we discuss in review in last class. And then the one of the topic which was supposed to learn in this course was not taught was the propagator. And this propagator is very important. Propagator is very important that you learn in QFT. But it was not taught in your earlier semester. And last class I defined what is the meaning of a propagator, how it is important, and also we calculate for a free real scalar field. That propagator is nothing but the Green's function, and this Gp was 1 over p square minus m square. So this we calculate by taking the Fourier transformation of the Green's function starting from the real free scalar field, means the Kg equation. So we start from a Kg equation in presence of source. From there we so do you have this? This was the top material I already taught you in last class. So if you have any question queries on this, please let me know. Otherwise, we'll start today's class. So you don't have any question on this. Okay, good. So so let us see the propagator little bit closely, that propagator, because I told you that when you do some calculations in quantum field theory, particularly we do most of the calculation in momentum space, and this propagator and basically when we do the calculation we need a integration over all the internal momenta. This in a particle can some internal particle, maybe this is not very clear right now, but for the time being you just understand that we need to do some integration of the momenta. Now and this quantity is propagator may come in the integrand. So if, or basically just let me tell you that if you have d4p and then 1 over p square minus m square, then there will be a problem. Let me explain what is the problem. This integrand, see, if I make this 1 over p square minus m square can also be written as 1 over p0 square minus ep square, right? That I p square is p square plus m square. No, this is 4 vector. So 4 vector p square is 3 vector p square plus, wait 3 vector p square plus m square but then okay, just a moment. Okay, this is P0 square. Now P0 is not energy, actually P0 square plus P vector square. So if you write your P0 square plus P square, then P0 square minus, so 4 vector square is the 0th component square minus 3 vector square. Now this term and the m term, if you combine, then it will give you the EP. Okay, EP square is P vector square plus m square. Okay, so this is the quantity. Now P0 integration, if you try to perform P0 integration, then this is a singular integration. Singular means it has this integrand is diverging. For example, suppose I have an integration -1 to +1 dx by x square. Apparently you think that okay, this is very simple integration, -1 over x, -1 to +1. If you calculate, you will get -2, the answer. But this is wrong, completely wrong, because this integrand is from -1 to +1, and there is a point in between, in this interval 0, where this integrand is diverging. This is also you can see from that if you plot this 1 over x square, it is like this. So at x equal to 0, so the integration is curve area under this curve, right? So this area is not finite. So how you get -2? Okay, so that is the whole point. So this integrand that defined is not appropriate. So we need to little bit take care of it, and Feynman, because the field theory is mostly developed by Feynman, and he said, okay, then you can do that GP, you can write limit, say epsilon going to 0, you wrote 1 over p square minus m square plus I epsilon. So I put a I epsilon and then I perform the integration, and then after the integration I'll take the limit. So this is the interpretation did by Feynman, and mathematically this is fine, no problem with that. I put a terms to remove the divergence, and after performing the integration I take the limit. Okay. So this is Feynman modification. So this is basically the pole or the diverging point will be shifted. P0, you know, P0 is basically the related, we'll see that it is related to energy. So energy is always positive. So P0 integration, if you perform the P0 integration, suppose this is P0 line, so minus EP to plus EP you have to perform, no, minus infinity to plus infinity you have to perform, and you can find this is the pole at minus EP and plus EP. Now if I add I epsilon, this will be shifted from here. So you can and this kind of technique you have done many times in your contour integration when you perform. Okay, so then Feynman defined that. So let us write this is a Feynman propagator, and let me write in now coordinate space also. So coordinate space, yeah, in coordinate space. So it will be limit epsilon going to 0, d4p 2 pi to the power 4 e to the power minus I p dot x minus x prime, all are 4 vector, p is also 4 vector, and then p square minus m square plus I epsilon. So this is the propagator, and here I will not do the mathematics. In this propagator there are 4 integration. You can perform the P0 integration, which is a problem sum. So that integration you can perform through a contour integration, and you get a result. A lot of calculation is there, contour integration, which I am not doing because this is not a directly part of this syllabus this semester. But just a moment, I don't know why my this was disconnected. My iPad is disconnected. I don't know why. So let me share it again. Okay, so this integration I will not perform, but you can follow it from some elementary books like say Lahiri and Pal, or if you have difficulties, you can tell me. So okay, so can you see my screen?
Yes, sir.
Yes, sir.
Okay, okay. Yeah, it was disconnected from my iPad. Okay, so this is this P0 integration is problem. So Feynman simplify this integration by performing the P0 integration and obtain a result which I am going to write, and this result is important for our this course. So I, there is I complex unit I multiplied with this, and this result was come out to be very simple, and of course lot of algebra is involved, but let me define. It is related to the field variables. I'll explain. So this result coming from here to here, it is I can put as a homework one. Those who are interested, you can do, but if you are not interested, then you can skip also. But then you have to assume that this result is this. So now let me explain what are this. This I use a tau here. This is called time ordering operator. You have known time reversal operator. Now this is a time ordering operator. For the first time probably you are hearing this name. So what is the meaning? It is very simple. It ordered the time, who is the initial time, who is the final time. So I have two operators, suppose a and x t, and say b x prime t prime. X is 3 vector, and okay. So this will be a x t, b x prime t prime if t is greater than t prime. So the operator which has the more t, letter t, will come first, and the operator who has less t will go in the second. T greater than t prime. So this, and it will be b x prime t prime a x t, the result of this, if t prime is greater than t. Okay. So in general, this you can write. So this, and this is your vacuum. So this is kind of expectation value. Expectation value with respect to vacuum. Vacuum means ground state in the field theory. But this vacuum at the initial time, so t is minus infinity, and this is again vacuum at t at the plus infinity. That means I had the system in the equilibrium initially, then I have my field theory, my time evolution, and again I will achieve a equilibrium at after long time. So before long time, before the we do our activity, the system was in equilibrium. After finishing our activity, system again will be equilibrium. So those ground state, those equilibrium are the ground state at minus infinity and plus infinity. So the Feynman propagator is nothing but time order product of the field variables, time order product of the field variables phi x and phi x prime, and its vacuum expectation value. So this is called the propagator, Feynman propagator. And what is the physical meaning that we are going to see? But before that, time ordered phi x and phi x prime, I can write mathematically. This mathematically I already defined. So mathematically I can write using theta function, theta t minus theta function. I'll define what is the meaning of theta function, times phi x phi x prime plus theta t prime minus t phi x prime phi x. So this is the meaning of theta function. Means theta t prime is 0 if is 1 if t greater than t prime, greater than or equal to, and 0 if t less than t prime. So that means in this case t, see x means, now x I am writing 4 vector, x means x3 vector and t, x prime means x prime 3 vector and t prime. Okay, so that you have to understand. So this has a t, this has a t prime. Now t greater than t prime, this will survive. So that is why, so time ordering I have break into 2. So time order operator you can write in terms of theta function. Theta function you are familiar, is that it is 1 when this argument t greater than or equal to t prime, and it is less than 0. So if I have a mathematical quantity then. So now what we are going to do, what is the physical meaning of this propagator? So now I can write my propagator I delta f x minus x prime, and suppose now suppose t greater than t prime. So t greater than t prime, which theta function will survive? This one or this one? Shivam Mishra, can you tell? So this is a theta function, this is same. Now I am assuming that my time t is greater than t prime. So which will survive? According to definition is written here.
First term, sir.
First term will survive. Very good. And when t prime is less than t prime, this will survive. So I am now, to have a interpretation of the propagator, I am just taking this condition and want to see. So in this condition, this will be my vacuum expectation value. T also will not be there. First term will be surviving. So phi x prime, and okay. So this will be there. And when I have t prime greater than t, I will have this Feynman propagator will have vacuum expectation value phi of x prime, phi of x. The other one will survive. So we have to see the meaning of this or this. So let us consider the situation first, t greater than t prime, greater or equal. Equal is also same thing. Okay, so now recall what is your phi quantum, that after quantizing we obtain a phi. If you don't remember the full form of the phi, but you should remember that there was a dqp integration, that a 2 pi e to e factor etc. If you don't remember, that is no problem. Then there was the ap e to the power minus ip dot x plus a dagger p e to the power plus I p dot x. So sometimes you confuse which term will be plus, which term will be minus. Easy to remember, dagger is like a plus, so dagger time will be plus. Okay, dagger is like a plus, almost like a plus, so this dagger term will be always positive. Okay, exponential power. So now what is the meaning of, we are considering that t greater than t prime situation. That means we are focusing on this. So I have phi x prime. So phi x prime. So let me write phi of x prime. So this will have a x prime. This will have a x prime. Okay. Now you can see phi acting on the vacuum. So you know AP acting on vacuum is 0 because AP is the annihilation operator, and AP dagger P acting on vacuum will create one particle with momenta P. That we know. So this time, so at t prime, so what will happen at t prime time, a particle with momenta P is created, because phi prime x is we are concentrating this. So phi prime x equal to 0. So this term will be automatically 0 because a p0 is 0 and a dagger will create a particle at t prime. T prime is your earlier time. So at the beginning some particle is created. Now what is the meaning of this? Now this acts on the dual space, bra space. Okay, so it will now you know the AP in the bra space will survive, right? This will contribute, and this is the meaning of that a particle is destroyed, right? So this okay, so a dagger P, now a dagger P acting on this will, the meaning is the destroy of a particle. So now meaning of the propagator. So meaning of the propagator, for meaning I am considering t greater than t prime. Propagator is the amplitude of a particle is created at t prime and t prime is earlier time and destroyed at time t. So it is basically amplitude. Propagator is basically amplitude, or you can alternatively you can think that that particle is being created at t prime time and that particle is destroyed at t because t is greater than t prime, and this amplitude of this process is given by the propagator. Similarly, when we consider t prime greater than t, particle will be created at t, t is the earlier time, and so this is creation. So let me write with the upper arrow, destroy means down arrow. So this is, or okay, no, it's more confusing with spin. Okay, so this is created and this is destroyed. Here t prime greater than t, particle will be created at t and destroyed, and vice versa. Vice versa means particle okay, that vice versa means t greater than t prime. So okay, so no need of vice versa here, I am just explaining here. Okay, so any question on this? So we get a physical meaning of the propagator. Mathematical part we that how to derive that Feynman propagator we have not discussed, but we know the propagator is basically amplitude. This understanding you should have, propagator is basically amplitude, because in quantum theories we all the time calculate amplitude and probability, right? Amplitude mod square is the probability. Okay, so this is all about the
So that will be creation of a particle, isn't it?
which one?
Their dagger is there, a dagger of P.
No, a dagger of P when acts on the brass space, it is again a destruction. See, this is a P acting on the Kate vacuum will be 0, and a dagger P and the Kate, this is the will be P. Now if you take a complex conjugation, so this will implies the bra a dagger P will be 0 again, but a dagger we know the creation kind of thing, right? But that is in the Kate space. In the bra space, that is a annihilation.
Okay, sir.
Good. Any other question? Okay, so this is the meaning of the propagator, and I think propagator, if it is asked in some interview what is a propagator, I think you could have you will have enough thing to say. Propagator I told you in classical mechanics, propagator I told you in quantum mechanics, which I'll elaborate little bit quantum mechanical propagator when I'll teach path integral of quantum mechanics. And now we can calculate the propagator in the canonical formulation, and we'll also calculate propagator in path integral formulation. Now, in this remaining class, I want to spend the time for propagator for the electromagnetic field, because that is important actually. It has a lot of non-trivial things. So let us spend some time for the propagator for the photon field or electromagnetic field. Quanta of electromagnetic field is photon. So let us take the terminology. Photon is the quanta of electromagnetic field. So propagator we want to, and this is some expression which will be using in this quantum field theory many times. You will also be using. So that let us try to again I will not do the whole mathematics, because it will not be possible to cover all this. So how you do? So those who have missed the first lecture also can follow this lecture, such that you can understand the meaning of propagator. See, we started from the Klein-Gordon equation because it was free scalar field. So we have to calculate photon propagator, we have to start from Maxwell equation. So let me write Maxwell equation, which you all have calculated in presence of source. This is the two of the non-homogeneous Maxwell equation. So let us start with this, and this equation is the Maxwell equation, you all familiar. So this Maxwell equation I can write mu nu and write in terms of this will be a box operator times G lambda mu, here only lambda, so how I can, okay, G lambda mu, and then this term will be del mu del lambda times a mu equal to j lambda. This you can simplify this. So this is the Maxwell equation. So we can start. So suppose our Green's function in this electromagnetic field d mu nu, because now it is a vector field. Photon field is a vector field. Vector means it will have an index. So its Green's function will have two index. That you, because it is propagate from one point to another point. Propagator meaning. So it must have two indexes. So let me x and x prime. So this is my propagator or Green's function for this differential equation. Okay. So when I take a differential equation, I'll tell it is the Green's function. When I talk about a field theory, differential equation corresponding to a field theory, we'll call it propagator, but they are same. So again, this by definition, so this is Green's function, or so Green's function, and by definition Green's function, this box operator G lambda mu minus del mu del lambda, a will be replaced by this propagator. So let me write the mu nu x minus x prime will give you the delta function, delta 4 x minus x prime. And now see this side, I have chosen my indices in such a way that it is not a scalar. There are two free index, one is nu, one is lambda. So that also has to be taken care of. So this is the definition of the Green's function for the vector field. Compared to earlier case, this factor is additional and there is no minus sign this time. Minus sign, I told you that by convention, this can itself give some minus sign, so we cannot take minus sign in this case. So this is my definition of Green's function, where this is my propagator or Green's function. Okay. Now we'll try to calculate. So let us calculate the propagator in the momentum space. Okay. propagator in the momentum space. So I'll take a Fourier transform. So Fourier transform and define this. So propagator in the momentum space. So let me write the mu nu I use mu nu x minus x prime should be equal to d4p 2 pi to the power 4 e to the power minus I p dot x minus x prime, and then I'll have the momentum space propagator d mu nu of p. Okay, so this is basically the Fourier transform of d mu nu p to get a coordinate space. So this is the relation. You can take an inverse Fourier transformation to get this. But now let us use the definition of the Green's function. So I operate this operator in the both side of this equation. So if I operate in the left side, I'll get in the left side g lambda nu delta 4 x minus x prime. I am operating this operator on this, so left side I'll get this, and the right side will be d4p 2 pi to the power 4, and then this operator acting on this. And this is a function of momentum, so this is only a coordinate operator, so it will not but remember this derivatives all are in with respect to x, not with respect to x prime. So okay, so only x will be differentiated, not x. So d mu nu p. So this is outside this differentiation kind of thing. So now if you perform this calculation, this is very simple, 2 times differentiation of the exponential function. Here also 2 times differentiation, but they are different index. So you can get, I can directly write from you know how to do the differentiation. So it will get minus p square g lambda mu, and this side you will get plus p mu p lambda. That again will be minus, but minus minus plus, because when you differentiate 2 times, minus I will come 2 times, minus I into minus I. So minus minus minus, so this will be minus. So that is why this term will be minus and this term will be plus, times d mu nu p e to the power minus I p dot x minus x prime. But left side is a delta function. So this quantity, delta function times g lambda nu. So this and we know the definition of delta function, d4p 2 pi part this integration. So if I have this integration alone, this part and this part, I'll get a delta function apart from this. So this part will be simply nu lambda, g lambda nu. So minus p square g lambda mu plus p mu p lambda d mu nu p should nothing but g lambda nu. This is 4 vector notation. You will feel little bit comfortable directly, will not feel comfortable because of the index, but if you do yourself, these are very straightforward and simple. So I can think of my momentum space propagator. Let me, this ink is not so bright, so let me go to red. So d mu nu p is basically your g lambda nu and divided by, not divided by, we don't need to write divided by. So this is the, so how you calculate now suggest that how we can calculate d mu nu p from this relation, because this calculation is little bit important, the techniques how we use, that is why I am doing this calculation. And this is also very simple, it's not very if it is a lengthy calculation, it is difficult to do in this whiteboard. So that is why this calculation is simple and not very lengthy, so that is why I am doing. Okay. Now, what will be the, see, directly this making, this is a tensor. So you have to basically invert a tensor, but inverting a tensor is not that straightforward. This is also kind of a tensor, so this is a bit tricky. So there is an indirect way. So I'll tell you how to find indirect. First is that what will be the general structure? What will be the most general structure of this? I have most general structure of a rank 2 tensor. So rank 2 tensor I have to construct out of momentum space. So I have to, what are my in hand? I have G mu nu, this tensor is there, and I have a P mu. As many times as I can use these two to construct this. So general structure, let us, it is a rank 2. So one possible term is G mu nu, where A can be any function of momentum plus I can have 2p. So let me write Bp times P mu, P mu, P nu. So this is one possibility. Now let us think of any other possibility. C. I can have G, say mu lambda, P lambda, and say P nu. Okay, this is possible. This is contracted. I have two index. I have to match two index, mu and nu. So it's possible. But this is nothing but this. If you think of this term, then this term is nothing but P mu P lambda nu. But P mu P nu term is already there. So in fact, you try to construct any other term out of these two terms by using as many times as you want, you will never get any other new term. So general structure of the propagator using G mu nu and P mu only, because these are the only two candidate for the momentum space. P mu is the only momenta and this is metric tensor. So nothing else. So this is the general structure of the. Now we try to find what will be our A and B by putting in this relation, comparing them, then I can find our propagator. So this is the whole idea. So anybody has any doubt about that? This is the most general structure. Because this argument is important. This is the most general structure, and if you have this structure, then you can put it here and compare left hand side, right hand side to find this propagator. So anybody has any argument or any difficulties to understand this argument? Whatever term, you can use 3 times G mu nu, 5 times this, try to get a index mu nu, because I have to match mu nu index. When I have a equation, left side index should match with the right hand side index. Otherwise, my equation is wrong. When we check our copies assignment, we always check that student calculation. If I find mismatch, oh, it's doing wrong. Okay, good. Think of it. Even if you have some question on this later stage, please bring it.
Why third term is eliminated, sir? Please again.
Okay, third term, there in principle can be infinitely many terms. So let me write the third term again. C function of P, some constant, arbitrary constant. Then I said that it is, say, write mu lambda, P lambda, and P nu. This is index is matching with the left hand side. Mu nu, here also mu nu, lambda lambda is contracted. So this term Now we know how to raise or lower a index. So this is lowering index formula. So this formula is Cp, then P mu, P nu. So these terms, this C can be added to the B. So this is the same term. So that is why C term is not considering. This is my arbitrary, na? So any other term you consider by using 3g mu nu, 2, 5 mu, or whatever it is, all term will be simplified to either this term or this term. So that is why I call this is the most general structure. So now I'll put this structure here and I'll try to find, and there will be a surprise for you. So let me use red. So minus p square times g lambda mu plus p lambda p mu. Then I'll write this a p g mu nu plus b p p mu p nu, and this should be equal to minus g lambda nu. Where my equation? This is my equation. Okay. Okay. Now it is simple. You just multiply this term. So first, if I multiply this with this, so g mu nu and this side g lambda mu. So there is a properties, whether I don't know. So you have g lambda mu and g mu nu. So mu is contracted. So this is basically g lambda nu. So this is for metric tensor. Prove these properties yourself. Just take a okay, you can expand and prove left hand side, right hand side, or any other way. Okay. So first term, when I take this and this, I'll get minus p square g lambda nu. Very good. Now this term and this term. Okay. So what will happen? Minus p square, then g lambda mu, p mu. So g lambda mu, then p mu, p nu, and b, right? This term. But p mu and p nu, p will be raised. So this term you can write a p lambda term. This is raising formula, right? Mu contracted, so p lambda. Okay. Now let us consider the this term is over. Now this term and this term. Okay. So plus a p g mu nu, again lambda mu, again mu contracted, so nu, this is lowering, this will be lowered to nu. So p lambda and p nu. Now final, the second term here, second term here. So plus bp and p lambda as it is will be there, p mu contracted, so it will be p square and then p nu. Okay, these four terms. Now look at the term, this term and this term. Right hand side is my g lambda nu. This term has a b, this has a b. This term has a p square, this term has a p square. This term has a p lambda. Here these two terms, when you combine these two, it is p lambda. This term has a p nu, it is p nu. So this term will cancel with this term. So what I remain with? P square g lambda nu, and the last term. Oh, there is a missing somewhere, no? This term has a ap. First term, no? This multiplied this a was missing. So ap, and last term was again ap, p lambda p nu equal to g lambda nu. So now let us compare left hand side and right hand side to get this term. So this term and this term can be compared coefficient. So minus p square ap. should be 1 from here. And if I consider this term and no such term in the left hand side with p lambda p nu, so AP should be 0. From here, AP is minus 1 over p square. From here, AP equal to 0. So, which is not acceptable. I am getting, comparing one term, I am getting AP equal to 0, and I am comparing AP from the another term, I am getting AP equal to minus 1 over p square. So, this is wrong, impossible. So, this is impossible to find a propagator. This is wrong, something is wrong, because left hand side, right, but we have not done anything wrong. We follow the same procedure as we followed in case of scalar field theory. Only thing here we did a general structure, because inverting the tensor is not that easy. Okay, the problem I mentioned in last semester also, this problem is due to that electromagnetic field has only 2 degrees of freedom. Electromagnetic field has only 2 degrees of freedom. But we are, when I considering mu field, mu equation, I am considering mu equal to 0, 1, 2, 3. So, all 4 degrees of freedom. So, there is a mismatch of degrees of freedom, and this is the problem of quantizing electromagnetic field. Even if you calculate pi 0 will be 0. So, pi 0 commutation with A0 supposed to be non-zero, but this becoming 0, right? If pi 0 equal to 0, this commutator will be 0, but this is the canonical commutation relation for electromagnetic field, and right hand side should be something non-zero, expected non-zero. So, again there was a problem in canonical quantization, there is a problem in to find the propagator, and all these problems are related because we are considering more degrees of freedom than actual. The system has only 2 degrees of freedom. Rajiv, can you explain how electromagnetic field has only 2 degrees of freedom? This I told many times in the last semester also, and can you, how this, they asked in this, in the interview, that how you will explain that electromagnetic field has only 2 degrees, how you understand that?
Sir,
It
because
should be explained for, tell me.
when we define the electromagnetic field tensor F mu nu, then we get only the terms, all the components in terms of electric field and magnetic field.
But electric field can have 3 components, magnetic field can have 3 components. So, there are 3 degrees of freedom from electric field, 3 degrees of freedom from magnetic field. So, they are supposed to be 6. But I said that electromagnetic field has only 2 degrees of freedom.
So because it has 2 independent components, and all.
But where
all of
are the
them
two independent, electric field and magnetic field? But electric field itself has 3 independent components, x, y, z. So, no, that is not the cause. See, this I explained, I am explaining for the last time. See, this when you have the, remember the Maxwell equation, divergence of E is something to related to rho. Curl divergence of B is something to 0, and divergence of now curl of E is plus 1 over C del B del T is also 0, and there is one more equation, then curl of B is related to J and del E del T. Okay. So, these 2 equations are the, this is current defines magnetic field, charge density define electric field. So, these are the 2 equations which define electric and magnetic field, but these 2 equations are the constraint to the electric and magnetic field. They put a constant. Electric field cannot be anything. Magnetic field cannot be anything, but its divergence has to be 0. So these are the 4 constant, because this is scalar equation, 1 constant. This is a vector equation. So vector equation means 3 component. X component, Y component, Z component, all are 0. So this 4 equation, 4 constant equation, and there are electric field has 3 degrees of freedom, magnetic field has 3 degrees of freedom, 6 degrees. So 6 degrees of freedom minus 4 constant, so 2 degrees of freedom. So we have less degrees of freedom, and we are considering more degrees of freedom. Now this problem can also be understood from here. When I consider this equation, you know there are other Maxwell equation, but you have not considered that. You remember del mu g mu nu equal to 0. This gives this equation is inhomogeneous equation, which correspond to these two equation. These two equation. These two equation. But where is these two equation? These two equation is del mu g mu nu, that dual tensor, and this equation you have not considered. Constraint equation you have not considered. So that is why you are getting a wrong answer to your propagator. Okay. So I think it should be clear. You think of it. If you have not clear, just listen to my lecture again, this part, and it should be clear. So what is the solution for it? Solution is very simple. That also I told you in the last semester. So let me tell you about the solution, that how to make the electron. So solution is that we need to reduce the degrees of freedom. How we will do? By gauge fixing. What is the meaning of gauge fixing? Meaning of gauge fixing is that, okay, see, gauge fixing means putting a condition like del mu mu equal to 0. This is called low range gauge fixing. This Lorentz is different Lorentz from the Lorentz transformation. Lorentz transformation, Lorentz LORENTZ, here NZ. There are two Lorentz. That all Lorentz are not the same person, that people do common mistake. So this is the Lorentz gauge fixing. So I put a condition on A. So A has 4 degrees of freedom. If I put a condition, it will have a 3 degrees of freedom. So 1 degrees of freedom will be reduced. But still there will be one more extra. But in right now, if we reduce 1 degrees of freedom by putting this, then you can have a good propagator. Good means well-defined propagator. You can have pi 0 not equal to 0. So these are the two problems we facing. Pi 0 cannot be 0, then commutation relation cannot be satisfied. So that also. So gauge fixing, putting this condition equal to 0 is effectively mean that your Lagrangian should be, earlier your Lagrangian was f mu nu plus j mu n mu. This is source term. Now if you put a additional condition, that is equivalent to put a term del mu a mu whole square. So if you put this condition, means that you are putting this additional term in the Lagrangian. Now if this is the additional term, find equation of motion. Gauge fixing I will tell you a little bit more in the next class. Today I want to finish this mathematical part such that in the you can do this exercise. So now if you have this Lagrangian, now you can find the Euler-Lagrangian equation that you are now habituated to do. You will find that box times a nu minus 1 by 1 xi del mu, where is my equation? Del mu del nu del dot a this equal to J nu. So please find this equation, your home assignment 2. If this is the Lagrangian, find that this is the equation of motion. Now, in using this equation of motion, please redo the derivation of propagator. That what the propagator I do the today's calculation, you redo this calculation and you will find the propagator G mu nu. Now you can find your A and B, those two coefficient well defined. You will get that 1 over p square times G mu nu minus 1 minus zeta p mu p nu by p square. So then first find this equation, then second find this equation, which is your home assignment 3. These are old topics, so that is I putting in home assignment. Those who are interested, they will do this, they will learn better. Those who are not, those who feel that they are in pressure little bit, they can assume this result. These are you can standard results, so you can. So this is the propagator. So maybe I'll stop here because it's 10 o'clock and we'll have some discussion on this propagator. Then we'll move to the next topic. So do you have any quick question? Otherwise, we'll this class is over. So you have understood what you have to do, that if Lagrangian density is given, where from this Lagrangian density I got by gauge fixing. So if you fix, then you find equation of motion and then that equation of motion. Now you have modified equation of motion. Because of this modification, now you will be able to find your A and B, which was earlier B was getting cancelled and A was found inconsistent result. So now you will find, and then from there you can find this propagator. So this is the propagator for photon, electromagnetic field, photon propagator. Okay. Any question? See, I already mentioned in the group that timetable is not correct. It has given Thursday 11 to 12 a class, which is also parallel to your compulsory course. So if you attend my class, you will not be able to the compulsory course, or if you attend compulsory course, you will not be able to my class. But this whole timetable committee cannot understand this, so they have not changed it. So I have shifted my that particular class to 9 to 10 on Friday. I'll follow the timetable exactly for your Tuesday and Thursday. Only Thursday 11 to 12 class, which is overlapping class, will be shifted to Friday 9 to 10. Let me know if you have any difficulties in 9 to 10 class, but this is convenient before beginning the day. If we have the field theory class, then it will be better. So I have already sent my schedule, which I'll be following strictly, independent of any holidays or anything. So that is Tuesday, Friday 9 to 10, Thursday 10 to 11. Okay. So this class is over. Okay.